Okay, so now let's see what conjugated dynes do. We just established they're slightly more stable than non-conjugated dynes, thermodynamically stable. Question is, does that translate also into kinetic stability? And this is a perfect example that you have encountered already in Chem 1 and Chem 3a, where the principle that is brought home to you that thermodynamic stability doesn't necessarily mean that something is not reactive. Thermodynamic stability is heat of formation data, okay, relative to some other compound. Kinetic reactivity refers to its behavior in our environment, in the presence of oxygen, let's say, or in the presence of a particular reagent. And we find that actually conjugated dynes, while they are relatively stabilized relative to non-conjugated dynes, are actually more reactive. And the reason is that if you look at the mechanism, the intermediates that you form are also stabilized by resonance. And here's a case in point, classic Markovnikov addition of HCl. So this is Markovnikov with a twist. Here we have just butadiene, the simplest dyne that you can write. You treat it with HCl, the proton hits on the right to form the most stable carbocation, which of course is the allylic carbocation. And of course you get only one cation, even though you could have two positions to attack, namely the one that gives you this allylic cation. This allylic cation has two resonance forms, and is then trapped by the chloride that's in solution. You notice that when you do this, since this is an unsymmetrical allylic cation, you get two compounds. When you add to the internal carbon, HCl has added formally across carbon 1 and 2, it's called a 1,2 addition. When you add to the terminal carbon, that's formally called a 1,4 addition. Now it turns out that 1,2 addition is faster than 1,4 addition. And here, unlike the radical case, which is murky, so I didn't want to delve into, and you guys are good, you started asking these kinds of questions, is there a difference in reactivity, and can we predict which isomer of these two chlorides will be formed preferentially? And here, because it's a positive charge, the more highly substituted positive charge is more stabilized. Here this rule holds quite well, and so therefore this resonance form is a stronger contributor than this one, meaning in essence there's more positive charge on this carbon than on that carbon. Chloride, being the nucleophilic species, it just sees two ends, one of them is more plus than the other. Coulomb's law, I go for this carbon, faster. Okay? So more rapidly you form this. Every now and then it will attack at the terminus, slower. Now diabolically, this is a case where the product that's formed faster is actually less stable than the isomeric product that's formed less rapidly, more slowly. Okay? And the reason is, to a first approximation, simply the more highly substituted double bond is more stable than the less substituted one. So this one is more stable than that. But this one is formed faster. Okay? Simply because in the intermediate cation, we have an unequal charge distribution. The chlorine goes beeline for the more positively charged carbon, not caring a damn at that stage what it's going to make. The chlorine doesn't realize that it's going not as downhill as it potentially could to a more stable product. It actually forms the less stable product more rapidly. Look at the movie of that. Just to give you some breathing space, there's HCl approaching butadiene. It protonates at the terminus to make the allylic cation. It's in resonance. A delocalized allylic cation. It's unsymmetrical because of this metal. So the chloride can attack here. This is actually more slowly because this carbon is less positive than this one. Attack at this position is faster. But making the terminal double bond is actually thermodynamically less good than attacking in such a way as to make the more substituted double bond. So let me give you a little cartoon which may be useful to illustrate kinetic versus thermodynamic control. Here is I or you, and we're standing in front of two tables. One is loaded up with fantastic desserts. The other one is loaded up with health food. Okay? Now, if you're like me, I go beeline for the sweets, okay? And start stuffing myself. Many of you, I've shed those qualms, but many of you, when they're doing this, will say, this is not really healthy, okay? I should really, you feel guilty, okay? So that's thermodynamically, psychologically unstable. Okay? So you retract, you retreat. Okay? And more slowly, you wander over to the health food. You eat the health food, you feel happy. Okay? Thermodynamically, more stable, but kinetically, you were drawn very rapidly to the unstable scenario. Okay? So let's look at this in terms of a real experiment, and which was actually an experiment that confused people when this was first run around the early 20th century. When people treated butadiene with HBr. If you ran the reaction at 0 degrees, you get one ratio, 70 to 30, of the terminal double bond versus the internal double bond bromide. Okay? It turns out, and then if you run it at higher temperatures, you got a different ratio. Okay? So that was bizarre. Moreover, when you took the 0 degree crude reaction product, 70-30, and warmed that up, that mixture started changing the ratio such that in the end you arrived at this ratio. Okay? Clearly now we know a case of kinetic versus thermodynamic control. At low temperatures, the intermediate cation, the bromide, attacks the internal carbon, which remember there's a positive charge here to begin with, has more positive charge here faster. You get more of this, less of that. At 0 degrees, these two guys do not go back. They do not undergo SN1 reaction. Okay? They're stable. Okay? So the kinetic ratio persists as long as you keep the temperature low. The equilibration of these two is slow by SN1. If you warm this up, if you run the reaction at 40 degrees, or you take this mixture and warm it to 40 degrees, now these allylic bromides will undergo SN1. They will dissociate back to the precursor allylic cation. And since you're now under thermodynamic control, eventually the more stable isomer in our equilibrium mixture will dominate. And so you change from 70-30 to 15 to 85. That's one way to show this. There's another way to show this, namely here. Butadiene HBr. First step, protonation. You get the two allylic halides. More plus charge here than there. Kinetic control is bromide attacks here fast. At low temperatures, this back arrow is very short. It's sitting in the kinetic product position. A little bit goes over here. Every now and then it does hit the terminal carbon, and you get this bromide. And that's also stable. So that ratio is the initial ratio we saw, 70 to 30. As you warm up, the kinetic product starts going back to where it came from because the reverse arrow starts being active, as it were. Okay? And so it goes back and forth, and now it has enough time to go over the slower process, or undergo the slower process to the more thermodynamically more stable product, and then the reactions under thermodynamic control, and the thermodynamic product dominates. There's a third way to show that, which is actually, in my opinion, the best. You show a potential energy diagram, where you're starting in the middle with the allylic cation that you get by protonating butadiene. Incidentally, here's the electrostatic potential map of this guy, and you can clearly see that this carbon, meaning that carbon, has a much larger blue area than this carbon. There's more positive charge on that carbon, so that shows up very nicely. And so bromide, as a nucleophile, is red, is drawn to blue, and that bromide, as it sees that menu, is clearly drawn faster to that carbon than it is over here, even though attacking here gives the less stable product. Okay, so we start here with this potential energy diagram. Now, I don't know whether you remember what these things indicate. They really indicate sort of, in a very general way, reaction progress along the so-called reaction coordinate. I like one way to picture this in your mind, which you may find useful. You think of all the minima, product here, this intermediate here, product here, as buckets, okay, that are connected by these lines, which are rubber tubing. Okay? So you have a construct with 3 buckets, and this represents height. So this one is the highest position bucket, this one is the next higher, this one is the lowest. You start out with this bucket here, which is the allylic cation. And the allylic cation is represented by water. So you pour in a glass of water. That's your allylic cation. That's what you form when you protonate butadiene. What is that system going to do in a potential energy diagram like this? So in order to mimic heat, meaning kinetic and vibrational energy, which makes these reactions go in the first place, you take your construct and you start rattling it. Okay? So what will happen to the water in here? It will start swapping up and down. Okay? Every now and then, if you rattle it fast enough, it will reach this point and then roll down into the lower lying bucket. Notice that this is higher, so less water will run over in the even lower, the lowest lying bucket. So initially, that's 0 degrees in the HBr reaction. This guy will form a lot of this, mainly this, and sit there, because if you rattle this just enough for the water to climb up that high and then drop down here, it can't climb back out of it, okay? Because this is much lower. So the distance from here back up here is way bigger than the distance from here to here. So it sits there in a kinetic, as a kinetic product. Only when you now start rattling like crazy, okay, 40 degrees, the water will start swapping around, go back in here, and now since you're overcoming this height, from here overcoming this is relatively easy. So eventually all the water collected here will fall into the lowest lying bucket. That is the simple-minded approach to kinetic versus thermodynamic control. Now, can we extend this? Yes. But because extended conjugation to trines, tetraenes, pentaenes, while it imparts even further thermodynamic stability, every conjugated double bond, every one of these bonds here, gives you an extra 3 to 4 kilocalories per mole, the systems become more and more reactive. Really bizarre in a way, okay? Counterintuitive. Because the intermediate radicals, anions, or in this case cations, if you hit it with acid, are even more highly resonance stabilized. So hexatrine, when you protonate that, forms a cation that has 3 resonance forms, they're all reactive. Okay? Hexatrine is, in fact, in practical terms, so reactive that when you buy it from Aldrich, and we did this over several times, half the time when you open the package, it's just black gunk that you look at in an ampule, because some traces of something in a sealed ampule cause the thing to just polymerize. Okay? So they become very hot, and therefore they're synthetically less useful, with one exception that we'll discuss on Thursday. The big difference occurs when you do cyclic conjugation. And the most stable system in this, or the most famous system in this, is benzene, which, when you look at the molecular model, notice now becomes actually a totally symmetrical cyclohexatrine, with all of the electrons delocalized over the 6-membered ring. And that is the subject of 3 chapters that we'll start with this in chapter 15. So there's actually unusual stabilization, because when you look at just resonance pictures, we have 2 resonance forms that are equivalent, that indicate that this should be an unusually stabilized system. And indeed, this, even though formally it's a cyclohexatrine, is actually quite unreactive with respect to catalytic hydrogenation, electrophiles, oxidation, and the like. So we'll deal with that on next week. Nature has a lot of conjugated systems, just a couple of them. I understand that you had electronic spectroscopy, UV visible spectroscopy in 3A, and you may remember that as you start putting double bonds next to each other, the HOMO-LUMO gap gets smaller to the point that the energy is small enough that these compounds are colored. Okay? So they hit the visible spectrum. And so here, for example, this guy, which is really an extraordinary 3, 6, 9, 11 double bonds in a row, is only stable because of all these methyl groups that protect it sterically from decomposition. That's the orange color of carrots. It's called beta-carotene. Okay? So that's where the orange comes from. When you degrade this is why people say carrots are good for you. You cleave it in half, you get this guy. This is actually vitamin A, also called retinol. When you oxidize this alcohol to the aldehyde, it forms retinal, and that is a key component of your eye. It's involved in vision. Vision, in a nutshell, meaning that when a photon impinges on a construct of this hanging off a protein called opsine, you get cis transisomerization. And that change, which is dramatic structurally, causes a nerve impulse that then translates into a signal that you then perceive as vision. So it's all organic chemicals that make you see. So all conjugated systems. Here's an unnatural system developed in the 70s by these characters here, got the Nobel Prize for this in 2000. Namely, they asked the question, hey, if conjugation means that one end of a carbon system, can communicate with the other end this is nothing else than a conducting metal. Okay? So can we have organic molecules conduct electricity? And so they did a very neat experiment where they took acetylene and polymerized it to polyacetylene. Okay? And they did another neat trick. They actually doped it with a little bit of iodine and pulls out an electron to generate a so-called electron hole. And that system showed conductivity that rivaled that of copper in other metals. And that's why there was a Nobel Prize given for it. Here's a little sheet of polyacetylene. Look at this. Looks like aluminum foil, right? But it's purely organic. And the future is now already here. You know, I grew up with this discovery, and then now, 4 years later, it's all over the place. All of these devices, these light-emitting diode devices, are based on conjugated polymers, based on extended pi electron systems where the electrons just sit up and down some long polymer chains. And the future is not too far off that indeed we're going to replace all of the wiring that we have with organic polymers. So we'll leave it at that for today. I'll see you all on Thursday. Thanks.